In this work, we introduce Granularity-Controllable Interactive Segmentation, GraCo, a novel approach that allows precise control of prediction granularity by introducing additional parameters to input. This enhances the customization of the interactive system and eliminates redundancy while resolving ambiguity. Now, we present several examples of granularity-controllable interactive segmentation. Firstly, we demonstrate the flexible granularity controllability of the method. Then, we demonstrate the precise control of fine-grained segmentation expansion. Current IS pipelines fall into two categories, which are single granularity output and multigranularity output, respectively. The latter aims to alleviate the spatial ambiguity present in the former. However, the multigranularity output pipeline suffers from limited interaction flexibility and produces redundant results. To address this, we aim to achieve granularity-controllable interactive segmentation, which introduces a granularity control parameter to the input to explicitly constrain the model. For instance, the granularity can be controlled by a value ranging from 0 to 1, where a lower value corresponds to a finer granularity and vice versa. Nevertheless, the exorbitant cost of annotating multigranularity masks and the lack of available datasets with granularity annotations make it difficult for models to acquire the necessary guidance to control output granularity. To acquire the any granularity masks and granularity annotations at a low cost, we design an any granularity mask generator that is fully automated and does not require any additional manual annotation. Specifically, AGG consists of two key components: a mask engine and a granularity estimator. The core of any granularity mask generator is the automatic generation of abundant mask granularity pairs. To achieve this goal, we exploit the semantic property of the pre-trained IS model to segment local concepts and object parts by simulating appropriate interaction clicks. We propose the multigranularity loop simulation to automatically simulate the human-in-the-loop mechanism and generate diverse interaction signals to drive the mask engine. To estimate the granularity of the masks, we design the granularity estimator and establish computational rules from both the scale and semantic perspectives to ensure that the model behavior is consistent with human cognition. At each loop iteration, the click simulator takes a negative click from the current mask and appends it to the click set. The current mask is then updated with the model prediction. After the loop simulation, the mask engine generates abundant part proposals with diverse granularity. All coarse-grained and fine-grained proposals are saved after post-processing, which involves morphological processing to eliminate mask holes and connected component filtering to select the connected part. Based on the mask granularity pairs generated by AGG, we develop a simple yet efficient granularity-controllable learning strategy, which incorporates the granularity embedding into the input and employ LoRa technology. This enables the IS model to efficiently possess granularity controllability while maintaining the original IS performance without requiring extensive computational cost. We transform the granularity into the learnable embedding as an additional prompt to the IS model. The prompts, including granularity, clicks, and mask, are integrated with the image embedding and jointly fed into the feature extractor. We compare our results with previous single and multiple granularity IS methods on 4 object-level benchmarks and 2 part-level benchmarks. Based on the results, single granularity IS methods show satisfactory performance in object-level benchmarks, but poor performance in handling the part level, and the multigranularity method perform poorly at both levels. In contrast, our GraCo achieves superior performance on all benchmarks at both levels. We also evaluate the performance on SA1B. We conclude that simple click performs poorly on such a multigranularity benchmark, while SAM achieves excellent performance because it is a subset of its training set, which is in line with our expectations. Our GraCo achieves comparable NOC 90 metrics to SAM, while significantly outperforming simple click. This demonstrates the robust generalization and excellent performance of GraCo in multigranularity segmentation. To demonstrate the necessity of both semantic and scale granularity, we conduct experiments in two settings, with scale granularity only and with both scale and semantic granularity. We conclude that the optimal granularity tends to be skewed to 1.0 when employing both scale and semantic granularity. This aligns with the granularity definition for the whole instance. To demonstrate the effectiveness of the GCL strategy, we evaluate the contributions of its two key components, that is, granularity embedding and low-rank adaptation. We conclude that incorporating granularity embedding effectively enhances the performance, whereas the LoRa technology preserves the original performance of the pre-trained model. Considering that the segmentation mask after the first click directly affects the user experience, we evaluate the IOU1 of the IS methods. From the results, we conclude that fine-tuning with part annotations leads to a significant decrease in IOU1 on object-level benchmarks. We observe that SAM exhibits excellent performance. Specifically, the first click performance of SAM is significantly superior than simple click, especially when selecting the optimal mask from multiple outputs for each instance. We also conduct an ablation study on the proposal sampling. We compare the performance of uniform sampling to inverse proportional sampling with identical mask proposals. The results show that the inverse proportional sampling method achieves a superior performance on all benchmarks. To verify the granularity controllability of our GraCo, we calculate the IOUK at different granularities and plot the IOU granularity curves. For 3 object-level benchmarks, IOUK increases with increasing granularity, especially IOU1, which is as expected. For the part-level scenario, we randomly select 3 part categories belonging to the cow category for validation. For highly detailed parts such as the right front upper leg and left eye, GraCo performs optimally at a granularity of 0.1. For coarse-grained parts such as the head, the optimal granularity for GraCo is around 0.6. The part-level results further demonstrate that our GraCo possess granularity controllability consistent with human cognition. We randomly select several parts from Pascal part annotations and automatically generate the next click according to the evaluation protocol for visualization. We find that simple click requires multiple clicks to segment the desired mask in multigranularity scenarios. In contrast, our GraCo requires only a single click to match expectations well based on roughly estimated input granularity. This demonstrates the flexibility of our GraCo to adapt to diverse scenarios. We also demonstrate the qualitative results of the proposed GraCo on 4 object-level benchmarks with a fixed input granularity of 1.0, and our GraCo achieves impressive qualitative results. Thank you for your watching.